Well, good morning from Boston. Give it a few more seconds just as people are joining the webinar. I can see we just started going live. So we start in a few seconds. Great. So welcome to Machine Learning Meeting Retail webinar with Professor Shah. My name is Babak Safari. I'm part of the support team at Emeritus that helped designing the course. You may have seen my demo. I'm gonna have one webinar next week for you. But today we'll be hosting the webinar with Professor Shah. It's my honor to do so. I'm looking forward to it. Couple of bookkeeping notes. We're gonna go live. We're gonna start the webinar. We go around 40 minutes or so. So we would leave the last 15 minutes to 20 minutes for Q&A. So if you have any question, please use the Q&A and type your questions. And I'm gonna go over all the questions, take notes, and we will discuss them towards the end. There will be a survey towards the end of the webinar after you log out. Please take that survey. It's very important for us to know your feedback. With that, I would ask Professor Shah to start the session. Thank you so much for your time in advance.
Okay, well, thank you everyone for joining wherever you're joining from. Good morning, good afternoon, good evening, and hopefully it's not too late where you are joining from. As Babak mentioned, I'm Debabrata Shah. You might have seen my video so far during the class, and I'm really excited to tell you today about machine learning, in particular, machine learning in the context of retail. Just as a sort of quick introduction of what I want to talk about and why I want to talk about machine learning in retail. Really, at the end of the day, there are many machine learning AI challenges that have been put out. In particular, some of them that we have observed in popular press such as self-driving cars and AlphaGo Zero, that is the Go player. Those are great challenges and those are amazing things to achieve. However, over past 6 or so years, I've spent time very closely in the space of retail, in particular building machine learning analytics solution for retailers. And I feel that the challenges out there are enormous, and at some level, one of the amazing goals for machine learning statistics and AI would be building what I would call self-driving retail. And if we can do a self-driving retail, I think there will be one of the way bigger milestone than actually identifying cats and dogs or just doing a self-driving car or flying a plane. And what I want to do in this webinar is give you a brief sense of why I do think that way, why I do think that sort of retail is an extremely exciting opportunity for people thinking about machine learning, both folks thinking about machine learning as a user of machine learning and bringing that to retail, as well as people who are trying to develop new methods in machine learning as an academic, as a researcher, and why retail provides really interesting next sets of goalposts, so to speak. With that, sort of, let's dive a little bit deeper into it. So as I mentioned, I'm a professor in electrical engineering and computer science. I'm a member of Institute for Data Systems and Society. I head the Statistics and Data Science Center at MIT, which is an academic center for statistics and data science, broadly defined. Machine learning is what I teach. For example, right now I'm teaching graduate machine learning class on campus. Founded a company called Select with a C. It's this is where I spent a lot of time in retail because the primary business of Select is to build machine learning solutions for retail. And last summer, very proud to say that Select became now part of Nike, the shoe company. And through that experience that sort of I've come as an academic, I feel that I've come out thinking really, really highly of retail, especially where retail and machine learning meets. So with that, let's go back to our basic view of machine learning. And again, in this course, we have focused on thinking about machine learning as going from data to decisions. And that is the primary objective that sort of we have viewed as the goal of machine learning. You have data, you want to bring insights from it and use those insights to make decisions. And the entire course has been organized around this as a theme. And the first thing you want to do, or even before you start, is you want to make sure that you have data in one place. Once you have data in one place, the next step is to understand your data well. That is, understand sort of what's happened in past. Then the first non-trivial thing comes around is to questions that what will happen? What will happen in the future? Once you understand what will happen in the future, you want to use that to make decisions. That is what you would do. And once you understand what you can do and what you did, you made certain decisions, you made certain choices. Now you want to understand whether it worked or not, what you can attribute to and what you cannot attribute to. In particular, somebody went to a store, utilized a coupon that they found and bought something. Did they buy because of the coupon, or they were going to buy and they just used coupon on their way? That attribution is difficult, and that's actually what comes out to be a causal inference. And again, once you sort of get all of these information together, you want to constantly evolve in your decision making. That is, this is not just one short process, but it's an iterative process that continues. So again, what will happen, what to do, and what the attribution part. Just to remind ourselves, the way we have sort of thought of what will happen is about prediction. The set of terms we've used and learned or we are learning are supervised learning, semi-supervised learning, unsupervised learning. What to do is the next place where we are thinking about decision systems, Markov decision processes, reinforcement learning, model predictive. All of these things we spent a lot of time discussing in this course. Then finally, in causal inference, of course, randomized control is the natural place where if we can do experiment, we would like to do that. But there are scenarios where we cannot do experiment. Sometimes you observe data where data itself has natural experiments done for you, and that will be great. But sometimes you just have observation data, and from there you want to do causal inference. You want to think about causality indices, etc., which sort of helps you understand what's happening. These are, again, very high-level overview of recall of how we have this course and how we organize this course. Now, what I want to do is I want to project all of these things in the context of retail and understand what are the questions in terms of retail. What is the data? What are the insights that we can get from data? What are the prediction problems? What are the decision-making problems? And what are the causal inference problems? And then I will spend some time discussing in detail prediction software, or what I would call prediction database, an abstraction that has emerged because of looking at retail-like data for us, and I will spend some time discussing that. And again, we'll touch upon some of the mathematics related to that, some of the algorithms, and some of how do you implement that. Okay? And then finally, we'll end the lecturing part of the webinar, and then we'll move on to the question and answer. So with that, let's get started. So again, so thinking about prediction is about given historical data as we have known, we want to use that historical data to predict unknowns when in future we come across an observation. So putting it another way, it's about taking features as input, targets as output, and model that we learn is what we care about. And that's what is about prediction. For example, in a setting where you have a historical data, which says different individuals, their demographic information, and then their life expectancy information, and maybe using this historical data, we want to learn some form of a linear model, a linear regression that maps demographics to life expectancy. So a new person comes in, we know her or his demographic information, and then based on that, we want to say, well, this person is likely to live so many years with this much of a confidence. Another example of prediction, which is time where time is an important component, is designing GPS. It's like you have a noisy observations of location of a given vehicle. You as an individual walking on the road with your phone in your hand, your noisy locations, and based on that, you want to figure out where you are precisely. And you want to use all the historical history and the current position to figure out where you are. Of course, there's a popular word called Kalman filter. In a sense, in 60s, this came around, and this is what led to navigating things like Apollo, leaving the Earth and reaching the moon, because it's a very noisy information you get about where it is, and based on that, you want to sort of decide where to go. Things like image is my input, a complicated neural network, which will tell me whether that image contains cat or dog, or that image contains a digit, and if so, which of the 10 digits it contains. And that's a classification task, and that's also a form of prediction problem. And going to retail, when we start thinking about this prediction problem in retail, really, there's only one. There are many problems, but if you look at, in a sense, retail boils down to having ability to do granular, very accurate demand forecasting. That is, given a product or a SKU, I want to know in a given geolocation, at a given price point, in given time interval, what is the demand? How many people will buy it? What will be the distribution of that? Understanding that, if we can have that very, very precisely, if an Oracle came and told me exactly how many of these set of trousers at this price in this store are going to be sold, what I will do is that on that day, I will make sure that exactly those many trousers are available on the shelf, no more, no less. They will be sold. I will not be holding any inventory in my system, and that will be amazing retail. My profits will go through the roof. Price on the stock market will go through the roof, because inventory turn would be effectively instantaneous. Of course, this is hard. And the reason this is hard, not only hard, it's extremely hard. It's one of the most challenging prediction problem I have come across. And it is very hard because data is extremely sparse. Just to put it one way, think of the data that you have in retail, such as different customers buying things, the customer information, the product information, the location information, etc. Really, the core for demand prediction is transactions, sales. If you look at that data, and if you put customers as rows, products as columns, and think of this as an Excel file, and if you put a black dot in a cell, if that row corresponding to that customer and column corresponding to that product had a purchase, one or more, let's say. And now if you sort of put this on a white wall, what the whole sheet would look white, because the number of interactions are so few. And that's actually one way to think about how sparse this data is. And that's why it's very hard to predict what a customer would do for a given set of products and vice versa. So the whole goal is, how do we sort of make this happen? And in order to make this happen, what we want to do is not only want to use transaction data, but we also want to do unstructured data. So what sorts of unstructured data you might want to use? Well, one way to make this happen when data is sparse, there's only one solution. You use other auxiliary data to stitch things together. One way to stitch auxiliary data together is data about people, data about product, and data about location, and how you get all of them together, how you fuse this information together. That's what matters. And that's, in a sense, is sort of what we did, for example, at the company I founded, and that's a way to make it successful. Okay. And again, sort of this view suggests a natural prediction as a software, which our natural data fusion environment. And I will briefly describe abstractly what this might look like later in the webinar. All right, so again, thinking at a very high level, there's a prediction, decision-making, and causal inference. And what we spend time is discussing what roughly prediction is and what it would mean for the retail. And again, many of these things you have seen before. Hopefully what you're seeing in the context of retail and exemplifying it in that way helps you make a better sense of it. Now let's move to the next thing, that is decision making. Okay, here the goal is you've got lots of historical data telling you something about the state of the world, the state of your decision making system, environment, framework. In those historical situations, you took certain decisions and you observed certain outcomes. And really, the goal for you is to develop an algorithm, a policy that learns from these things and decides whenever new state is encountered and you've got a bunch of options.
And I'm like at the cross of 495 and Route 2 in a town called Littleton. So I'm like in almost central Mass. Okay, so Scottsdale, Arizona. Course content. So next week, we're going to be covering data visualization in R. So that is the ggplot library. And there are tutorials. If you have not yet set up R on your local computer, you want to install R, and then you want to install RStudio. Those are two separate programs. You need both. You install R first, then you install RStudio. And there's documentation and videos to help you through that. So in week, we go from there after we learn a little bit about confidence intervals and T-stats and Z-stats, we go into hypothesis testing. And so the example we'll give there is it's a fake example, but a pretty real looking data set of what it would look like if you ran a hypothesis test on an e-commerce site, testing if, saying that a price was at a discount rather than just saying, it's, 25% off and it's $75, or just saying it's $75. How do we analyze this test? How do we, design and scope hypothesis tests, and what are the test statistics that we want to be able to use? And of course, we want to be giving confidence intervals so that the business is aware of what the true interval really is. And so after we cover all of that, we're going to go into exploratory data analysis. And this is also where we'll cover data cleaning as well. So EDA is going to bring us a little bit back to obviously there's a lot of data visualization in EDA. So we'll be looking at univariate plots, bivariate plots. We'll be looking at correlations, all the different types of things you want to look at when you're doing exploratory data analysis to get an understanding of your data for modeling purposes. And then we will be also covering data cleaning as well, and recoding variables. And we'll be working with the data set that we'll then be using to build a logistic regression model with later on in the course. And so from there, then we'll go to linear regression. We'll build a linear regression model. We'll talk about how to interpret it in the output. The following week, we do logistic regression, generating predictions, creating testing and training sets, looking at the accuracy and the recall, and all the different metrics that we're worried about with logistic regression, and again, how to interpret that output for our stakeholders. Then in week 11, we build the very beginning of an interactive visualization. So there we're covering
which of these options should you take so as to maximize or optimize your objective of interest, maximize your result. Let's take one classical example. It's managing your portfolio. Let's say you have some amount of money, and as you must have noticed, if you are doing anything with financial market right now, it's a pretty interesting time, very volatile, depending on your perspective. If you're a passive investor, you don't like it. If you're a very active investor, you might love it because it's a volatility that allows you to make and gain money or lose money for that matter. So let's suppose you're an active investor. What you have is you've got some sum of money that is invested across some set of assets, and every day in the morning you wake up and you say, I need to rebalance my portfolio. Question is, how do I do that? Well, given where I am, given what history I've seen, and given what I see, what I can predict, because I've built now a nice predictive model of recent future, so to speak, that will tell me in next 5 days what's going to happen to S&P, for example, or things like that. Based on that, I'm going to rebalance my portfolio by optimizing my gains. And then tomorrow morning, I will wake up again and do the same thing for next 5 days, and so on and so forth. Okay, this is called model predictive control, and this is how you can do balance a portfolio. And again, you might find that this is somewhat sounds very commonsensical. Making it work in practice is very hard. Another extreme, let's sort of do a little bit gimmicky but really challenging thing called board of the game of Go. What you want to do is you want to design an automated game player, the Go player, that can actually take the board position of Go as an input, and based on that decide what next step to make. So that eventually, of course, your goal is to win against your opponent. And here you can actually train your neural network using historical data or whatnot to decide a policy. Now, in this course, as you may know, we discuss in detail how to design an automated Go player along the lines of the AlphaGo Zero, very popular in press, came out of DeepMind Google, and we will sort of discuss that, and that's sort of in detail architecture. Of course, I'm not going to sort of go down that path here. Now, coming to retail and thinking about decision-making systems in retail, I think the number of opportunities or number of challenges is just unbounded, because retail is such a massive organization. The predictive part, let's say you forecasted the demand at a different granularity, different levels very well. But now, as far as decision-making is concerned, you start from, in the retail, from decision-making, starting with day one of your decision-making cycle, where you, as in sitting in the CFO's office, trying to decide how do you balance, how do you sort of decide on your budget in terms of where you spend money on your inventory, how much you spend. For example, if you are a big box retailer and you say, well, how do you sort of spend money on clothes, et cetera, et cetera. Once those decisions are made based on historical data and what you predict in the future, you want to take that and then maybe go further down and say, okay, this is the amount of money that's decided to be spent on clothes. How much should go for men, women, pants, shirt, et cetera, et cetera. Maybe those decisions are already made. You want to go further down layer and say, well, somebody told me that I have to buy so much worth of denims. Question is that which sorts of denim should I buy? So the tight ones, the stretchable, et cetera, which brand, and so on and so forth. And all of these things are really decision-making questions, and the decision makers at some level, many humans are involved in the loop, and getting humans working with the data, working with the system is really, really hard, because humans are, especially in the context of retail, as I've found, there are some of the amazing people who work in retail who have great experience and history with the domain. Machines can only do so much, and it's a question that how do we bring humans and machine together? So at some level, for me, a great challenge would be getting model predictive control to work in entire retail would be huge, because that will work in sync with humans. And this will be actually a great step forward towards what I would call self-driving retail. Okay, so again, lots of opportunities, lots of challenges, and things like online real-time fulfillment or recommendation systems are getting automated, but they also need, I think, humans. And then as we move further and further closer to many human-driven decisions, such as merchandising and planning, I think there is a need for bringing machines and man together, or women together. Okay, so that was the part 2. There is, again, we discussed predictions, discussed decision making, and now the third part, which is causal inference, the attribution. What worked, what did not work. As we know, causal inference is about extracting causal connections between the conditions, causes, and the effects. Okay? So you give me historical data, you tell me what are the conditions you're interested in, and then sort of, I want to understand sort of what of those conditions caused the effects that you cared about. Okay. For example, the classical setting is understanding or evaluating efficacy of drugs. Randomized control trial, or RCT in a short form, is the way in which, for example, the government requires the drug or the pharmaceutical industry to evaluate the efficacy and report it. So let's say you have a drug A, I have a drug B, I have come up with this new drug, both of us treat the same sets of patients, and we want to understand, at least we want to evaluate and put it out whether B is more effective than A or not. Okay, how do we figure that out? Well, potentially I know that B works well for younger people and A works well for older people. So if I want to make a case for B, we will treat only younger people and give them B. On the other hand, if you want to evaluate favorably for A, we'll only give it to older people. And that's not right. What we want to show and argue is that which of these drug is better on average over the population. And if that's what we want to do, we want to choose randomly individuals from the population without determining which drug they're going to get, and then assign drug and patients to each other. That's how I would like to do drug efficacy. And also we would like to do it with placebo too, because we want to make sure that the drug works better than nothing. So that's how we design randomized control. And there's a beautiful history of this topic, more than 100 years. And this has become the industry gold standard. This is how people do A/B testing, so to speak, in the e-commerce to evaluate which algorithms or which recommendation or which promotions are better. But you cannot do this all the time. For example, if you're trying to study brain, you want to understand sort of which neurons fire after other neurons. So what neuron firing causes another neuron. And this is where methods like Granger causality or causality indices are built. Another beautiful example which actually led to an amazing thing, which is called London cholera outbreak. Potentially all of you know, based on some history lesson, that in London in 1850s, there was a massive cholera outbreak. It happened in what currently now known as Soho area. And there was a part where lots of people were dying of cholera and trying to wonder what is causing it, because the rest of the London was okay. And long story short, people realized that there was one water pump that led to cholera infection. And the reason is people were consuming water. So people first understood the relationship between water and cholera. And the way they realized is that there was natural experiment happening, that there were parts of London where cholera was there and they were drinking water from this pump. And there were part of London where cholera was not there and drinking water from other pump. And actually in that part, there were few people who were drinking water from this pump, they had cholera. It was a great natural experiment, almost like randomized control, but nature designed it. And then from there, it led to further investigation, which eventually led to discovery of bacteria. So the point is, causal inference can be as deep or as powerful and as influential as doing a fundamental scientific discovery like bacteria and subsequently antibiotics and so on. So causal inference is something that should not be taken lightly. It's foundational to everything that we reason logically based on data-driven manner. In a sense, if I were to sort of make a bold claim, well, I'm here and I can potentially make that, given that I'm potentially among friends here, is that if one were to think about how do we design policies to regulate social media platforms such as Facebook and Twitter and so on, I think causal inference has to help us understand that, and that can potentially help us design a data-driven methods to do that. Anyways, but potentially this is a discussion for another time. going back to our favorite example of retail, in a sense, variety on very hard causal inference question arise in retail. Of course, we discussed e-commerce, which is part of retail, and randomized control or A/B testing is part of it. But more importantly, there are harder questions. For example, some of the things as we were doing as a part of Select was helping physical retail stores. And let's suppose that I came to your store. So you are a physical retailer. You've got, let's say, hundreds of stores in continental United States. And I came and told you that use my approach, my method, my advice, and what will happen is that your revenues will increase. So I said, okay, fine, here's what I'll do. I'll take my New York store, flagship store. I will take your advice for that, and I will make changes to that. A year goes by or 3 months go by, and we check what's happening to the revenues. Well, if revenue increased compared to last year, I'll say, if you are a skeptic, you would say, well, this happened because economy became better. And if revenue went down, and if you're a skeptic, you would say, well, it didn't work. See, I told you so. Actually, it was bad. And if I wanted to make case against it, I would flip the bits here, and I would argue the same. The point is, nobody can win or lose this argument in a logical, undisputed, data-driven manner. Well, you say, why don't we go to randomized control? The problem is randomized control is not feasible. I mean, if you want to do randomized control here, I would need 10 copies of the New York store, same New York store. I mean, it's as ridiculous as it sounds. We can't have 10 copies where 5 are running my policy and 5 are not running my policy. There's only one store. So how do we think about it? There are methods people have developed. Some of the things I actively think about as a part of my research. Key term is synthetic control. For example, I'm going to do a tutorial on this at machine learning conference called NIPS or NeurIPS. And this is super exciting. And again, retail is provides, in my mind, a great sandbox for many such situations. So in a sense, if CRISPR has become what for genetics as a test bed sandbox for causal inference, I think retail also provides some such test bed for us to think about many of the policy style observational studies. Right. So with that, there was a high level overview and trying to give you an example of how things that we learn in this course can help within an organization like retail at different levels. Now what I want to do is I want to sort of spend a little bit more time going very precise in terms of how retail, for me personally, has changed in terms of how we have been thinking about the problem of prediction. And this has led to a very nice abstraction of what I would call prediction query language. And again, the whole reason for us prediction query language came into existence is the following. In retail, to make accurate demand forecasting for products, you need to fuse different types of data. And these fusion of different types of data changes. Right now, I have transactions and line browse information and maybe product information in terms of catalog information. Tomorrow, you might even provide me some demographic information about the places where things are sold. Maybe after some time, 6 months later, you will provide me Twitter information and whatnot. Maybe then you will provide me information about Pinterest. Maybe you will take away the Twitter because it is too expensive, and so on. So the point is that sort of you have this prediction system that you've built, new data come in. If I want to do traditional approach, every time things change, I have to rebuild the whole thing. And that's like a 6 to 8 months to a year's, a big data science team working together. It's a serious endeavor. No matter however good tools happen, it's work because you got to tune it. You got to sort of do this, you got to do that. So the question is there a way we build software system where if actually it may not be 100% accurate, but it'll be almost as good as the best thing you can design. However, it allows you flexibility of software, just like how we have databases. And that led to us to think about what I would call prediction query language. So how do we think about prediction query language? Well, one way to think about prediction query language is go back to the databases themselves. And one mental view of a database is a personal database. One mental view of personal database is Excel file or CSVs, just the way you see on the screen. So imagine I've got a data like this, which have 4 columns, bunch of rows. Each row in this data actually explains that this is a kind of a textbook marketing example where each row corresponds to marketing campaign. And what's happening is we just represented this data. And the type of questions you might have is that, well, given this, what is the sales? If this was the marketing campaign, what are the sales will be? If this is the sales I want and this is what I'm spending, what should I have in radio, and so on and so forth. Now, if we don't have missing values, there is no prediction problem. And all we're trying to do is that given sales value, I want to figure that value out. And that corresponds to traditional SQL queries or SQL queries. And it's like select queries, so to speak. So if you ever use databases or things like that, or any of the data analytics where you write free-form query, this is the type of question you are answering. When you're defining your table in a singular form, you define each column, like TV, etc. And one way to think about in this data set, you can say each unit of data is associated with a column name, and there is a key. The key is, let's say, the index, primary key, and then associated value. Okay, so that's how you view your data. And the query basically says that, tell me what is the value of this cell. If it was present, it's traditional query. If it's absent, it's a prediction query. Okay. And what you might want to do is, especially to answer prediction query, you might want to use multiple columns to put them together. Okay. And that's basically what I would call prediction query language. There's a unit of data is a key or tuple of keys with some operation which is capturing relationship, value associated with that, and the query is about predicting the missing value. For example, here is a set of 2 columns that I want to use, TV, and the way I will define this data unit is say 2 is this is the key number, there is a value which is null for another associated, TV is the name of the column, value is 230 point something, so I think this should have been here, pardon me for that, and so on. Visually, you can write down in this graph database-like form, okay, and when you're capturing, this is another table, another column, and so on and so forth. Again, I know I'm going very deep here in this webinar form, so it's likely that I'm completely, or you are completely missing the aspects of this. My hope was to give you a sense rather than explain the details. So be patient with me as I walk through this if you don't get the details, because that's not expectation here. Really, all I'm trying to say is that there's a clean way to look at your data and define what I would call schemas. So you as a user define these schemas. The schemas will tell you capture relationship between the columns which you are defining, and also the information that's present. For example, here is a nice popular movie lens data set where data has multiple tables. One table looks like this. There is a notion of movie, what is the name of the movie, and what is the genre. That is represented through these nodes. These are movie nodes. Their genre, and then maybe one is drama. This column is represented as movie with the title as another operation or column name and the name of the movie, and so on. So each node may have multiple such arcs of different colors. And then things like a user rating specific movie certain amount, that's captured through this relationship, an arc. And information about a tag that user gives is another arc between user and movie. And if there was a user information like a name, then there will be an attribute associated with that. But once you define this whole data can be viewed in an algebraic way as a 3-ordered tensor. Once you view the data in a 3-ordered tensor, really prediction problem boils down to what I would call filling the missing values in tensor, or what's called tensor estimation. Once you have tensor estimation, and you go back to the old classical statistics, there is a sort of the say which goes like a rose by any other gnome would be the same smell same. Of course, I'm sort of quoting Shakespeare here. But the point is that when you put that into perspective in this database setting, really all it says is that what you call precise keys or table name doesn't matter. It's the values that matter. And that leads to a very nice mathematical representation, which leads to a clean implementation in terms of neural network. Once you have that clean implementation, you can actually get the system working as a software system, just the way we discussed. That is, you have a data, you don't need to do anything other than define schemas. And this is where all the hard work comes. Once you have done that, step 2 is what system does. Then step 3 is where you just make prediction queries and you get the answers. And this way, more data comes in, data goes away, it doesn't matter, system remains the same, you don't need to rebuild. It's instantaneous. Okay. Again, one may ask question, is it meaningful or not? Well, this is what we did. There are 4 benchmark problems with benchmark data sets. This is the data set problem specific best solutions, and these are our solutions coming out of this software system. And again, this is, as you can see, it may not be best, but it's almost comparable, so to speak. And that's the thing we are wanting to take away. In summary, what we have done here is the prediction query language provides a prediction service as a software. It can be realized through deep connections to mathematical statistics, and then gets realized through neural network, and then becomes real. So it's always useful to think of questions in their totality, stepping back, but then sometimes something super simple happens like this. Okay? And again, so there's a beautiful mathematics that comes out of why this works, needs explanation, and this is a bunch of research that has happened for me subsequently over especially past few years. And if you're interested, feel free to sort of look for those things. They're available online. Okay? So with that, I think sort of we are closer to 10:40, and I think it's time for me to pause here, but again, leave you with the message that machine learning has made tremendous progress, but there's a lot to be done. And retail, in particular, self-driving retail is a great set of goalposts. And with that, let me sort of hold the baton back in the hands of Babak, and so that sort of we can sort of do question and answers.
Sure. Thank you so much for your time. Very informative webinar. I enjoyed it. I'm sure everyone else did as well. So let's go over some of the questions that came up in Q&A. Again, for those of you that maybe joined later, please use the Q&A so it's easier for me to keep track of the questions, and everyone else would see the questions that you mentioned. So I'm just going to start from the top. The first question was about the buzzword machine learning, and that everyone is trying to use it, even though it may not fit. How should we avoid this, or using machine learning when we were not supposed to use it?
I think sort of, you should ask for yourself the following litmus test. That is that, so okay, one of the things that machine learning helps you do is sort through your data, okay, understanding, use that data to make a succinct model of it so that you can do predictions. You can sort of try to use it to decide unknowns, and then use that to make decisions, and then use that further to do causal inference or attribution. Those are the high level things. Now look at your problem and ask yourself a problem, whether it's about understanding your data, whether it's about getting insights about your problem from data, or is it about making predictions. And prediction need not be forecast. It could be about unknowns, so to speak. That is, for example, I don't know Babak's age. Of course, there's nothing forecasting about it. It exists. It's just I don't know. Is there enough data that I have that I can use to actually do that? Maybe I can see him right now, and I have other historical data, and other historical data has some tags associated with that. So maybe putting that together, I might be able to say something reasonable about Babak's age. That's a litmus test I did. That is, let me look at a question, see if it fits into one of these high-level questions. Then let me sort of see, do I have enough data? And then maybe there's a hope. And then I can do cross-validation, so to speak, if data has enough structure, and from there I can decide what to do. So the point is that machine learning, yes, it's a buzzword. It's a buzzword because suddenly we have realized that there is this dimension in which we can explore things that we did not explore before. There is lots of computation available. There are lots of let's call it help available out there. And there's a lots of different types of data sets that have become available out there. So use it with caution. If somebody comes and tells you, can you predict the financial market crash right now? I think it's going to be an interesting challenge. I would feel it's just on the edge, because on one hand, we have historical market crashes. We have historical proxy signals that can help us understand, but we don't have that much of data that can help us. If somebody asks you and tells you, well, can you predict whether there will be alien that will be coming down on Earth? Well, God help you, because there's no data about that. On the other hand, if anybody asks you, what will happen to the climate tomorrow or temperature tomorrow? Well, we have a lot of data and we have lots of methods. So maybe that's a good place. So that's how I would at least put it. Again, I'm pretty sure I'm not answering your question, but hopefully I'm providing you guidelines to think about how you would answer your question.
Great. Thank you. The next question is about an example of model predictive control.
Absolutely. That's a fantastic question. Again, so let's just parse the three words. There's a model, there's a predictive, and there's a control. The control is basically a decision-making method process. It comes from classical control theory, like thinking about how do we fly planes and aeronautics and astronomy field, the electrical engineering world, and so on. So that's why control, but it's about decision-making. Predictive is you want to do prediction and then use that to do the decision-making or optimization. And it's a model that is you want to design a specific model to do the prediction. So the idea is that, let's suppose you have a model of how your system dynamics, so to speak, will evolve in future. You want to use that in a finite future, truncate it and use that to make optimization decision in terms of what you should do now. And that's basically what model predictive control means. Going back to the financial setting, you want to balance your portfolio. What you would do is that, well, you want to balance your portfolio so that you are rich forever, but forever is too much. Should you just look at once day? That's not a good idea, because who knows, things go down and come up again. So maybe that's not what you want to do. Or things go down and go down further, then that's not what you want to do. What you want to do is that you want to look at recent decent history for which you have reasonable predictive power and use that as a quotes in quotes your best guess, and then do optimization of decision now. That's what is model predictive control.
Great. Thank you so much. The next question is about the causal inference part and the time in the modeling that comes into effect. Is it before you do the machine learning part? Is it during? Is it after? So the question was roughly about that part.
Great point. So again, causal inference or causality is about what are the causes and what causes lead to what effect, right? So usually the cause happened before the effect. That's the the temporal causality structure. Now, question is that maybe the methods of causal inference, how do you think about them? If you're doing experiment design, saying that, let's say, randomized control, to understand what drug causes better outcome than other one, you design the experiment upfront. You don't look at what's going to happen to them. You don't contaminate your experiment design by looking at the outcome. Okay? It's like saying that you don't look at which sets of people my drug works better or worse. You don't do that. You just take your drugs, pick the people at random, assign them drugs, then close your eyes, let the things happen. Now you observe the outcome and use now machine learning to determine which worked and which did not work. And that's how you go about it.
Great. Thank you. So there were 2 or 3 questions regarding what we call data pre-processing or data cleanup, about missing values, noises, outliers. So people were interested to see what are common techniques. Also, there were one more specific questions of, is there a data visualization technique that can screen data for those anomalies?
Great. So I think just to at the highest level, right, there is a few questions here. All of them are about data processing, pre-processing. So let's just think of them one at a time. Okay, at the 0th order, you want your data into some place so that you can query it, access it. Data, though all of us teach assuming data is clean, data is never clean. Okay, data has unusual things. So first thing you want to do is that get rid of all the unusual things. How do you get rid of unusual things? Well, on one hand, you might have simple rules. For example, if you are measuring data about, let's say, prices, hopefully, unless you're sort of doing a terrible business or recording something differently, prices should not be negative. Okay? So have some simple rules to apply filters. The other thing you want to do is you want to make sure is that if you have predicting system available, such as prediction things, that can help you curate missing values, and then use those to understand sort of what are the high-level anomalies. Visualization is a great friend because it can help you understand that. Other way to think about it is that look at some kind of summary statistics of your data by subsampling your data. That is, look at 50% of the data at random, look at what summary statistics come out, look at another 50% of the data and see what summary statistics come out. If they are stable, then maybe data doesn't have too many unusual things. At least for the purpose of making ML decisions, it's not going to matter. So these are the type of basic sanity checks that you do. And once you have that, then you sort of put it as a part of your quotes and quotes pipeline, so to speak. And once you have that pipeline, that will come into your ML pipeline, so to speak, and then it will continue down the stream. Coming to another question about visualization, there are lots of great open sources. Open sources can help you visualize, of course, and then there are paid enterprise softwares out there for visualization that can help you, and you can just do Google search and you will find a nice large list of them, who are the industry leaders and so on. Now, these visualization software will simply plot things, okay? One way to think about any visualization software, it does two-dimensional plot. It cannot do anything more because our screen is two-dimensional. Maybe at best 3-dimension, but nothing more. So really, at the end of the day, the cleverness comes down into determining what 2 or 3 dimensions you want to plot and visualize. Okay. Sometimes you want to say, well, let me understand what is the average amount of sales happening in this zip code. That is a question that you are asking, and then you visualize it, and so on and so forth. And once you do those visualization, that might help you capture anomaly or not. To actually have anomaly captured through visualization, you need some form of machine learning as a part of it. And that usually is not available.
Thank you. And you said it all, but again, just to reemphasize that the quality of the data really defines the quality of your predictions and the model that you're getting. So it is a very essential step before you jump into the process. So there are many more questions. I'm trying to prioritize the questions which are more relevant to the topics that we discussed. So bear with me. Hopefully you will get to go over all the questions. But the next one that I was going to mention was about, sorry, I lost it for a second. It was about the movie example. That the movie example looks like a network structure graph system. Have you seen like benefits of using the network modeling part in machine learning over the typical machine learning example?
That's a great question. So I think I can see that here as well. So before I go down that thing, there's sort of somebody who has asked a very simple question about ML conference I was going to talk about.
Yeah.
You can sort of find online. So I'm not doing any publicity to this. It's called NeurIPS, NEURIPS. It's academically, it's one of the primary machine learning conferences where most of us as an academics go, and that's in December. So that's one quick answer. Okay. Now coming to an excellent question that this gentleman asked, Mr. Schroeder, if I read it correctly.
I removed it to the next page. Yes, it was about the network. It was Matthew. I was talking about the network structure of the movie data set.
Perfect. So you're absolutely right. At some level, when you're defining these relationship links, you're defining a kind of a graph structure, so to speak, or you're thinking of that as a matrix. And when you're stacking different types of data in that matrix form, you're getting a tensor. So really, it's that tensor or algebraic structure is what is really useful in bringing the quotes and quotes, the model building in an automated manner to the extent possible.
Great, thank you. So there was one interesting question down there for difference between demand sensing and demand forecasting.
Okay, so I guess, again, sort of, maybe I'm not 100% sure about the terminology, but if I were to hear the words you're saying and trying to make difference, trying to explain what I understand from there, demand sensing is about actually having sensors that can capture the information about demand. And demand forecasting is about telling you what's going to happen tomorrow. Okay, so for example, let's say I have a store. And say hypothetically, I've got these amazing cameras that are there everywhere in the stores, okay? And then I've got amazing amount of computation power and great sets of, let's say, computer vision, etc. technology that can actually understand and capture everything about who is coming in, what they're looking at, what they're buying or what they're not buying. That is, and then sort of actually translating it into machine readable thing. That would be what I would call demand sensing, okay? Demand forecasting is using this data now, today, tonight, and I telling you how many such people will come with what interest tomorrow.
Great, thank you. So another question which you kind of answered, so it could be a brief answer, would be how to get the market, economic, external conditional factors in our prediction models from Rohit here. And they say also by the time that the goods arrive, maybe the demand has changed. Well, how should we handle these situations?
Yeah. So I think this is a great question. There's another person who has asked the question about the time varying things because
so aggregations of one comes in minutes, one comes in daily and monthly. How do we aggregate that? So thanks for putting them both together in an answer.
Beautiful. So again, sort of, I think there are a few things here, right? So one is how do we get the auxiliary information in? That's one. Second is how do we deal with the time varying nature of it? And the third is different level of aggregation, so to speak, okay? Now, this is a large surface area to cover. So let me sort of start covering it one at a time, and then maybe we can sort of try to see if we can put all of them together. So first of all, as far as auxiliary information is concerned, going back to, let's say, that prediction query language framework, or going back to the retail setup, right? As I was mentioning, there are different types of data sets that you have. Data about transactions, data about people's browse, and now maybe data about these economic micro conditions. What you want to do is you want to stitch them together. So one way, if you believe in the prediction query language formulation I showed you, you can put them together as different slices of tensor, so to speak, with time being one of the axes in which things are changing, okay? And then what you're trying to do is that for a given time range, for a given type of metric, you're trying to figure out what is the right answer. Okay? So that's one way to sort of think about how you fuse things. So at the end of the day, whether you use the formulation of prediction query language or any formulation that you like, your favorite information fusion framework, that needs to be utilized to do that. Second, as far as time varying is concerned, see, a simplest example of this is like designing GPS or location tracking, right? That is, you are at certain position, you're going to certain other position. At each point, you're changing your location. But at each point, I'm going to try to tell you very accurately where you are, despite the fact that I have very noisy information about you. So how am I doing that? Well, that's what we are trying to do through designing a GPS, or what's academically known as Kalman filters. So putting it otherwise, some form of notion of filtering or dynamical system view has to come into play. Traditionally, the way machine learning is taught, it's all about deterministic static one view. That's a prediction problem. Decision-making system, when we discuss, it actually talks about certain dynamical view of the world. And it's that dynamical view of the world that is necessary to deal with this kind of things. Okay, so that's the second question. The third question was about different frequencies. Okay, so I wish I had that plot here because somebody was showing me that recently. You see, look at any sort of one, let's say there's a one measurement that you're measuring that's time varying. If you aggregated it, let's say daily, it would look something like this, okay? But if you went down at the finer aggregation, let's say hourly, it would look something like this. So it is following the same macro trend, but inside micro, it's changing quite a bit. The way to think of these kind of signals is it's a signal with, again, now I'm getting very detailed, but it is multiple harmonics, so to speak, multiple frequencies, okay? It's like I'm speaking slowly, and at the same time, maybe Babak was sort of doing this like zzz. So then what you hear is you're hearing a slow speak and then fast speak, zzz, and you're hearing combination of that, okay? So really the point is that if you have a good algorithms, then it will extract signal at both granularity from appropriately sampled data. And then what you want to do is that you want to determine which frequencies are relevant and which not by effectively looking at how much quotes and quotes energy of the data that you want to capture. Okay, now I'm getting too much into frequency analysis, time series, etc. And I'm not sure this is the right venue, but all I'm trying to say is that there's a way to deal with it. Putting it all together, this is about multi-dimensional sensor fusion problem with time varying thing with different characteristics. A lot of surface area. I hope I communicated some.
Thank you so much. So I think we have time only for one question. Some of the questions that you asked, we are right in the beginning of the course. So you would see that your questions would be answered with the more materials in the next weeks would be released in terms of examples on supervised or unsupervised or building the models. We have demos that you have the data set, you're going to build the models, and we would have more webinars which you would get a chance to ask your general questions about machine learning and AI. But Jay's question came very early, and I'm just going to wrap up with that question, which was about there are all these cloud services available. Google has one, Amazon has one, and so on. Are they specialized for a specific task? For example, in case of retail, do we have one which is more preferred than you're doing with retail, or like for NLP, for example? And I just merged that also with one other questions, which is very interesting, is like, do we have prediction as a service? I think compared to software as a service available as a commercial service. And that would be the last two questions.
All right, very quickly. So first of all cloud systems try to partner with different things. And I'm not going to sort of say any one of them is better than another one. The reason is there's a lot of context here and all that. All I would say is that, look, if you are interested in solving your problem, look for what is the best solution you can look for given your constraints. That is, can you actually have a team of data scientists with you, or can you have just one analyst who knows what to define, or you just want to fully outsource it? And that might determine where you will land up. Any computer is a computer, and most of these things are open sources, so you can simply get them in any environment, okay, depending on how much time and resource you want to get. Prediction as a service, definitely that's a great question. I think sort of there's a little bit more nuanced. My view of this is that there's no one prediction problem. So there's no one solution like a software as a service in a one deterministic way. However, I think analysts as a service, so to speak, is what I think is the right view here. That is not data scientists as a service, but analyst as a service. Think of like Excel as a like tool to solve machine learning problem is as a service. And it's one of my current passion right now. And I believe sort of really there should be one-click AI-like view of the world where, you know, depending on what you want, you do different clicks, but just once. But it's not, there's no one button that you press, and that's too much to ask for. Maybe 20 years from now, it'll be different, but at least as I see right now, I don't think that's it. Okay.
Thank you so much. Thank you so much for your time and the great webinar and all the answer. Again, sorry that we couldn't get to all your questions. Our time is limited. We did our best. Thanks for calling into the webinar today for all of you. Please don't forget to take the survey at the end. After you log out, there will be a link posted. And Professor Shah, again, thank you for your time. I think I'll see you in the next webinar.
Of course. Thank you, everyone, and good morning, good afternoon, good evening, and good night, depending on where you are.
Great. Program support, we can end the session. Great. Everyone have a great day.